Hey everybody, today let's talk about static electricity. You know, there's a lot of overlap in the world of static electricity in the everyday world that you experience. I mean, looking at these pictures, haven't we all walked across the carpet and gone to touch the doorknob and received a shock? We've all stuck balloons to ourselves to look silly. We've seen lightning and played with plasma balls. Look at this young man that's going down this plastic slide and receiving a static charge in his hair. And who hasn't had a bad hair day for ladies and some of you folks that care about that? We all have experience with static. I mean, you take your sweater off in the evenings in a dark room and you see the static electricity in it. These are all static electricity events that can only be explained by an understanding of the physics of electrostatics. Now, not only do electrostatic force occurrences go through all the events of everyday life, but without the forces associated with static electricity, life as we know it would not be possible. Electrostatic forces, both attractive and repulsive in nature, hold the world of atoms and molecules together. Without the electric force, material things would not exist. Atoms are the building blocks of matter, and they depend upon these forces. We're made of atoms, and we all the things that we do, the touching and feeling, smelling, tasting, walking, all of these things are a result of electric phenomena. So electrostatic forces are foundational to our existence. And if you look at this picture, just to review some basic chemistry from last year from atomic structure, we know that atoms have protons, neutrons, and electrons. We know that the protons are positive, neutrons are neutral, and the electrons are negative. Now we find the protons and neutrons in the nucleus of the atom. So the nucleus of an atom is positively charged, and these protons and neutrons are held together very tightly. But we also remember that the electrons move in these valence shells around the outside of the atom. It's worth writing down here a number that you guys are going to need to know. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. Coulombs is the unit of charge that we'll be using here. So the charge of an electron is negative 1.6 times 10 to the negative 19. But what about a proton? Protons have the same charge, it's just opposite in sign. So a proton has a charge of positive 1.6 times 10 to the negative 19. And this is a number that we'll be using quite a bit in this unit. All right, so let's think about items that are neutral versus charged objects. All right, if an item is positively charged, that means it possesses more protons than electrons. But I really don't like the way that sounds, because if we go back and look at the model of the atom and think about the nucleus, you can't add or subtract protons because the protons are bound in the nucleus. Plus, if you took away one of these protons, it wouldn't be lithium anymore. If you change the atomic number or the number of protons, it changes which atom you have. So when we look at this and we say that something possesses more protons than electrons, then what we mean is this particular object has lost electrons. That's how it becomes positively charged, is by losing electrons. So if an item is negatively charged, it possesses more electrons than protons because it has gained electrons. It's always the electrons that move around, all right? And if we have equal numbers of protons and electrons, that's self-explanatory. Now, some of the math that we're going to have to do in this unit is really pretty simple. It's just that the numbers seem odd to us. So if we have an object that picks up some excess electrons, so it gains electrons, it's going to have a negative charge. I wonder what the charge of that object is. Well, it's simple. This is the number of electrons we have, and we know the charge of an electron. So all you have to do is multiply 1 times 10 to the 6th by 1.6 times 10 to the negative 19. And let me do that real quickly. All right, now that I've multiplied that out, if you multiply 1 times 10 to the 6th by 1.6 times 10 to the negative 19, you get 1.6 times 10 to the negative 13 electrons. Or your charge. Okay? Now, what about protons? I wonder what the charge would be. And I guess before I do that, let me correct this. This would be in coulombs, by the way. That would be the charge. So if we have 3.5 times 10 to the 8th excess protons, we just make this positive and multiply, and let's see what the charge would be on that one. All right, after multiplying those two together, we get 5.6 times 10 to the negative 11. So that's a positive charge. Oh, I want that right. In coulombs. So as you can see, the mathematics that we do for this unit, at least in calculating the charge, is not terribly difficult. It's just that we have to deal with scientific notation. All right, so moving along, let's think about the activity of these charges. Like charges repel, and so if you have two objects that are positively charged or two objects that are negatively charged, they will have repulsive forces that act between them, pushing them apart. And it's only when you have opposite charges they're attractive. But as is always the case, it's not quite that simple. You know, if you look at these balloons and you think, well, I don't know what the charge is, what can we know about them? Well, if we look at this, repulsive interactions provide convincing evidence that both objects must be charged. So if one of those has a positive charge, the other one must have a negative charge. When it gets less or more confusing or less clear is when they're attractive. Now, you have to have at least one that's charged. So let's say that this balloon has a negative charge. Then what does that tell us about this one? This one could be positive or it could be neutral because of induction. All right? Now, what else could happen? What if this was positive? Well, if they're attractive, then this could be negative or it could be neutral. Because a neutral charge will have an induced charge and be attracted to a charged object. So you have to be careful with what you think you know about charge when objects are attracted. And let's see how that would work out in this case here. All right, so in case number 1, if we have two balloons, if we look at this case and A and B are attracted, then what do we know about that? Well, it says that B is negative. So what does that tell us about A? If B is negative, then A could be positive or it could be neutral. Because remember, neutral objects can be attracted to a charged object. All right, now if we know that B is negative and C is repulsed from it, remember that's conclusive evidence that they're the same charge. So C would have to be negative. All right, that wasn't too bad. All right, so in this second case, if we know that B is negative, then what does that tell us about A again? We know then that A can be positive or it can be neutral. But when we look down here at the bottom, then, well, let's see, that can't be right. Let's back up then. Think about this for a second. So if B is negative, but down here they're repulsed, what does that tell us? Then that tells us that A has to be positive because these two are repulsive, and so they have to be the same sign. So then C has to be positive as well. And I hope that makes some sense to you. All right, we'll wrap this up, and in the next video, we'll talk about some other properties of static charge. Thanks for watching.